In this video, we're going to examine the relationship between cell potential and equilibrium. So the standard cell potential for a redox reaction can be related to that reaction's equilibrium constant by the following equation, where here we have our standard cell potential and here we have our equilibrium constant K. In this video, we want to look at how we derive this equation and also how we can use it. So recall from a previous discussion that we talked about the Nernst equation, and the Nernst equation is used to calculate the cell potential when we have concentrations of reactants or products that are non-standard. The Nernst equation looks like this. Here we have our cell potential, and we relate that to Q, where our Q concentrations of reactants or products are something other than 1 molar. Also, we want to appreciate that the cell potential, if the cell potential for a redox reaction is positive, greater than 0, that reaction is spontaneous under those conditions. That reaction would have a delta G value that was negative. If the cell potential is less than 0, so you have a negative cell potential, then under those conditions, that reaction would be non-spontaneous and would have a delta G value that's positive. And if our cell potential under a set of conditions is equal to 0, and that reaction's at equilibrium, and the delta G value would also be equal to 0. So given this, if we have our Nernst equation, and this reaction is at equilibrium, so we allow the reaction to go to equilibrium, then we know that our cell potential E, not E standard, but E, is equal to 0. So we could rewrite this equation, substituting in 0 for our cell potential. Now let's solve for the standard cell potential. If we do that, rearrange it slightly, we get the standard cell potential is equal to 0.0592 volts divided by our number of moles of electrons transferred times the log of Q. Now also, since this reaction is at equilibrium, we know that Q is equal to K. So we could rewrite it as follows, where our standard cell potential is equal to 0.0952 volts divided by the number of electrons transferred times the log of our equilibrium constant. Now, just one quick relationship here. If you have a K value that is greater than 1, then our standard cell potential will be positive, and that reaction will be spontaneous under those conditions, under standard conditions. If the reaction has a K value less than 1, if we take the log of something that's less than 1, we get a negative value. And again, be sure you check this to prove it to yourself, but if you take the log of a number that's less than 1, you get a negative value. So that would give us a E standard that is negative, indicating that that reaction would be non-spontaneous under standard conditions. So let's take a look at an equation where we can use our relationship that we just saw, the equation that we saw between standard cell potential and equilibrium constant. Use the standard reduction potential to calculate the equilibrium constant for the following reaction. So let me put up a table, pause the video when I do, and try to solve this problem. Okay, so here we're asked to solve for K, the equilibrium constant, using our standard cell potential. So if I calculate my standard cell potential, I want to look back at my table and find my two half reactions. Okay. And these are the two half reactions that I want to use based on the equation that I'm given. So if I take those two half reactions, you can see here they're both written as reduction half reactions, but I can see from my chemical equation that I'm given that the bromine is being oxidized. So the bromine half reaction is being oxidized. So I want to flip that. And so that's going to be my oxidation half reaction. And the dichromate will be the reduction half reaction. So now I want to get these standard reduction potentials for each. Okay, so we can see those values here. For the bromine, it's 1.09. For the dichromate, it would be 1.33. So here I have my standard reduction potentials. We said that the bromine reaction, that's our oxidation half reaction. Remember, we have to have one reduction, one oxidation. So we need to flip that reaction, and when we do, we convert this from a standard reduction to a standard oxidation potential by converting the sign from positive to negative. So now, in order to get the electrons to balance, here you can see I have 2 electrons. In this one I have 6 electrons. So we need to multiply this whole equation by 3. Now that, again, reduction potentials or oxidation potentials are intensive properties. So if we multiply the equation by 3, it does not affect our standard oxidation potential. Okay, so remember that remains constant. So if I multiply through by 3, I get the following equation. You can see I have 6 electrons being lost, 6 electrons being gained. And now I can add those two reactions together to get my overall equation. And I can add my E standard oxidation plus E standard reduction to give me my standard cell potential. So I need that for my equation. And also, I've determined that I have 6 moles of electrons being transferred. So looking back at our equation that we saw earlier, we can plug in our standard cell potential that we calculated and our 6 moles of electrons. Now we can solve. So we solve this to get the log of K, and then we solve for K, and you see we get 2.1 times 10 to the 24th. K doesn't have any units, equilibrium constants don't. So you can see that this reaction has a positive standard cell potential, and we get a K value here that is much larger than 1. So that tells us that we've probably done this correct. So be sure you appreciate when to use this equation. Appreciate that we can only use it when we have a reaction that's at equilibrium. And also be sure that you can calculate these numbers correctly.